As buildings have been getting larger, earthquakes have become a bigger threat. An earthquake is going to affect a small hut much differently than a large building. The building materials have been greatly improved, and engineers have managed to utilize what they know about different materials properties in order to prevent total collapse of buildings during an earthquake. We are now also able to build impressive structures such as the one you just saw constructed in New York City.
When it comes to buildings, there are two main types of structures, reinforced and unreinforced. The building that you see being demolished now is unreinforced, meaning there is nothing to absorb the tensile stresses. This makes the structure very brittle. Next, you'll see the demolition of a reinforced structure via the same methods. As you can see, this wall is reinforced. It has steel rods embedded in the structure. These rods are called reinforcing bar, or rebar for short. The machines that knocked over the unreinforced wall so easily are having a lot of difficulty knocking over this wall. So how does this rebar make a difference?
There are different ways in which buildings get reinforced. Here are a few examples. As shown here, the concrete is reinforced with long rebar shaped into a cage, and in other instances, straight rebar is used.
The steel that rebar is made out of is generally 1020 or 1040 steel. This means that the percent carbon in the steel is about 0.2 to 0.4 weight percent carbon. When looking at the phase diagram, we can see that these are hypoeutectoid steels. This means that they're more ductile, but still strong, making them a perfect fit to reinforce concrete.
So what?
This reinforcing bar gives tensile properties to an otherwise brittle material. Before this bridge was retrofitted with dampers, it was able to oscillate from wind stress without rupturing. In addition to bridges, these qualities can also be given to buildings. Additionally, rebar affords greater strength with less material. This is quite important since concrete production accounts for 7% of carbon dioxide emissions worldwide. This video was taken during the 9.0 earthquake in Japan.
So as we can see, reinforced concrete is a composite material, and to recap, concrete gives it compressive strengths and the steel rebar gives it tensile strength. So what happens when things go wrong?
This was the Canterbury Television Building in Christchurch, New Zealand. It was built and designed in the 1980s and marketed to the city as having a new, innovative seismic design.
115 lives were lost in that building.
Liam Bartlett with 60 Minutes Australia tells us more.
Now, one of the key people responsible for its construction has been revealed as a monumental imposter. It turns out this supposedly highly qualified engineer is not at all who he claims to be.
This is Will Fisher, a structural engineer from England.
And this is Gerald Shirtcliffe, a major con artist.
Will Fisher returned to England and never saw Gerald Shirtcliffe again. Strangely, he never saw his engineering degree again either.
I couldn't find it. That was it.
It vanished.
Yeah.
Amazing coincidence, isn't it?
It certainly is.
Gerald Shirtcliffe used it on much bigger jobs, like one of Sydney's most iconic buildings, the 33-storey Kingsgate building in King's Cross, for which Shirtcliffe claimed to be site engineer in the early 1970s. Will Fisher, as he calls himself these days, has worked here in Australia for 25 years as a civil and structural engineer. His web of deceit unravelled by the deadly earthquake that destroyed the CTV building in Christchurch last year and devastated so many lives.
Obviously, this is a huge ethical problem with unknown ramifications. No one knows for certain how many projects he was on and how many buildings might be unsafe.
When Shirtcliffe reluctantly appeared by video link from Brisbane, he claimed to have been barely involved.
From the best of my recollection, I was on the site about once a month at most, and there was no need for me to visit the site regularly because it was essentially a straightforward job.
That staggering claim was met with disbelief.
Do you accept that you were responsible for all the construction activity as construction manager? Are you getting advice, Mr. Shirtcliffe, before you answer a question?
No, I'm not getting advice.
Shirtcliffe's former colleagues slammed his evidence.
I don't see how he could possibly have done his job as a construction manager by attending the site once a month.
Well, he just wasn't up to the job. You know, it's as simple as that.
Many factors played a role in the building's failure. There were numerous issues with design, but there were also issues with construction. A lot of the rebar that was supposed to tie in from the beams to the shear walls was actually bent back and not attached as shown on the plans. As shown here, this caused the slabs to fail in horrific ways. These slabs never should have rotated off the walls as they did.
These documents are from the report that was compiled by the City of Christchurch that illustrate the damages and root causes of the CTV building collapse, confirming the fact that multiple preventable factors played a role. One of these factors was the type of reinforcement used. There are two types of concrete reinforcement, ductile and non-ductile.
These are ductile connections from beams to column. In this instance, this allows the beams to give way before the columns do.
Ductile reinforcement is when the buildings use plastic hinges along the edges of the structure, that is when under stress, fail first, so that the damage is caused in a predetermined location. This is especially helpful in areas that are prone to earthquakes because there's a constant movement, and buildings that are non-ductile will show no failure under stress until it's too much and they just crumble. This is what happened on February 22nd, 2011, when a 6.3 magnitude earthquake struck Christchurch. It followed two smaller earthquakes in 2010 that caused damage and weakened the infrastructure. This earthquake killed 185 people, and out of them, 115 were in the CTV building.
The direction that the masonry fell showed that the masonry above the second story had already been stressed past its yield point. This is due to the first two earthquakes that occurred in 2010.
The problems with the CTV building didn't end there. The structural engineer working on the project was working beyond his competence. He had never built a structure exceeding 2 stories, and he had little experience using the modeling program that a majority of the designs were constructed on. Despite this, the principal engineer signed off on his designs and pressured the City Council to do the same. It's obvious that this project doesn't meet the triple bottom line.
This isn't a situation unique to the Southern Hemisphere. We have this problem here at home as well. A large earthquake struck the Central Coast a few years ago. As Felix with KSBW News reports,
I covered that earthquake 5 years ago and I saw that destruction firsthand. Today I saw a downtown Paso Robles completely transformed, rebuilt. Unfortunately, I didn't see the same at the Mission San Miguel or at City Hall in Atascadero.
Unfortunately, San Luis Obispo has not either. As you can see in this map of California, there are still a lot of unreinforced masonry buildings in San Luis Obispo County and in the city of San Luis Obispo, like the historic Fremont Theater. And in the previous map, you saw that California is at a high risk for earthquakes. You can see that a lot of these buildings have these warning signs in front, but that's not enough. These buildings need to be retrofitted. Do you want to wake up one morning, turn on the news, and hear this?
115 lives were lost in that building.